Welcome to Networks Professionals.
Okay, so if you've been amazed by what artificial intelligence can do lately, you're definitely not alone. You might be wondering, though, what was the specific spark that took these systems from, well, frustratingly basic to brilliantly capable almost overnight? Today in this explainer, we're looking under the hood of the most fascinating technological revolution of our time. We're going to demystify the transformer. This is the underlying architectural engine driving modern AI. And honestly, this isn't just about marginally better chatbots. No, it's about a foundational leap in computational capability that completely rewrote the rules of what machines can understand and generate. We're going to unpack the exact mechanics of this breakthrough and see exactly how it reshaped our modern digital landscape.
Okay, let's dive into this. It's truly wild to think about the timeline of this massive shift. The breakthrough we're unpacking today can be summarized perfectly by this quote: "The transformer came along and basically gave AI a massive brain upgrade." Because think about it, before the year 2017, the AI landscape was defined by some pretty rigid limitations. We were interacting with systems that were brittle, very narrow in their application, and often completely unable to grasp the nuance of human communication. The underlying mechanics back then just simply weren't equipped for complex, sustained reasoning. But then, researchers at Google introduced this new architecture. It served as an immediate fundamental upgrade to how computers map and synthesize human language, creating a really distinct dividing line between the rudimentary AI of the past and the incredibly powerful, dynamic systems we rely on right now.
Section 1. Before 2017, AI's memory problem. To truly grasp the magnitude of the transformer, we have to look at the frustrating bottleneck that paralyzed older machine learning models. Prior to 2017, systems like recurrent neural networks, or RNNs, were the standard. Now, these networks process text sequentially. They strictly moved one word at a time, left to right, much like how you or I would read a book. And while that sounds logical on the surface, it created a massive mathematical nightmare for context windows. Because RNNs process data in a strict linear sequence, by the time the model reached the end of a long paragraph, it suffered from a vanishing context window. It literally forgot how the sentence started. You simply couldn't feed these models a lengthy document and expect them to retain the core theme from the first page to the last. Transformers, though, they completely flipped the script. They abandoned that sequential word-by-word requirement entirely. Instead, they process all the data simultaneously. They ingest the entire sequence of text all at once, maintaining a perfect, uncorrupted global view of the information. This simultaneous processing was the elegant, paradigm-shifting solution to AI's most critical memory flaw.
Section 2. The secret sauce, self-attention. This brings us to the specific, awe-inspiring mechanism that mathematically solved this memory problem, self-attention. Now, what's really interesting about this slide is how it perfectly illustrates the issue. To understand why self-attention is so revolutionary, consider a classic natural language processing puzzle, often called a Winograd schema. Take the sentence, "The animal didn't cross the street because it was too tired." As humans, we effortlessly rely on real-world context to know that the word "id" refers to the animal, obviously, right? But older sequential models would stumble heavily here. Because they read sequentially, they might reach the word "it" and mistakenly link it to the street simply because it's closer in the sentence. The transformer's self-attention mechanism completely bypasses this vulnerability. Because it ingests everything simultaneously, it looks at every single word in that sentence at the exact same time and assigns mathematical weights to determine their relevance to one another. It calculates the relationship between tired and animal and instantly maps it to the animal, totally eliminating the ambiguity. It doesn't just read the words, it mathematically maps the underlying semantic structure of the entire thought.
Section 3. Parallel processing unlocks speed. Let's move to and see how this builds.
You simply cannot build a massive, complex model like GPT-4 if you're constrained to reading the internet one word at a time. The shift from sequential to simultaneous processing didn't just make AI smarter, it completely revolutionized how these models are actually trained. Because transformers severed that strict sequential bottleneck, they unlocked the raw power of parallel processing. And in the world of computer science, this is a monumental advantage. It meant AI researchers were no longer limited by the speed of a single processor working linearly. Suddenly, they could throw massive clusters of high-powered GPUs at the problem, distributing the workload and processing vast oceans of data all at once. The transformer literally turned a tricky language problem into a highly scalable computational problem. This sheer magnitude of scaling is exactly what allowed organizations to ingest effectively the entire internet. We're talking millions of books, articles, and code repositories, all in a fraction of the time it would have taken an old RNN.
It's the scale of this parallel processing that really forms the bedrock of today's cutting-edge models.
Section 4. Transformers expanding beyond text.
And this brilliantly illustrates how what started as a breakthrough in computational linguistics rapidly evolved to solve incredibly complex problems across entirely different scientific domains. You see, the true brilliance of the transformer architecture is its universal abstraction. To a transformer, a piece of data is just a token. It doesn't strictly have to be a word. Once researchers realized this, the applications just exploded. We now have vision transformers, or VIT, which treat small patches of an image the exact same way a language model treats a word. They apply self-attention to master complex image analysis and computer vision. In the audio space, this exact same architecture maps the relationship between sound waves, powering lightning-fast, highly accurate speech-to-text transcription. And perhaps most astonishingly, systems like AlphaFold are using transformers to predict protein folding. By treating amino acids as tokens in a sequence, the transformer applies its self-attention mechanism to decode the fundamental building blocks of biology. This is vastly accelerating the creation of new medicines and therapeutics. The underlying math just scales seamlessly across disciplines.
Section 5. Unpacking the GPT connection.
So the crucial point is, if you've used ChatGPT or similar platforms, you have directly interacted with this architecture. The famous acronym itself perfectly synthesizes all the mechanics we've just explored. The G stands for generative. This means the model isn't just, retrieving pre-written answers from some giant database. It's actively synthesizing novel text, code, or ideas by calculating the highest probability of semantic connections right there on the fly. The P stands for pre-trained. This highlights the fact that the model has already leveraged that massive parallel processing capability to ingest and map the relationships within internet-scale data before you ever even prompt it. It arrives with this vast baseline of map knowledge. And finally, the T stands for transformer. The very simultaneously processing self-attention engine we've been deconstructing today is the beating heart of the system. It's the very foundation that makes the generation and the pre-training possible in the first place. This architecture created a defining before and after moment in our relationship with computing. We transitioned practically overnight from an era defined by simple rule-based systems. Think about those clunky old autocorrects, or early voice assistants that totally lost the plot if you spoke for more than 5 seconds, into an era of truly dynamic intelligence. Today, we collaborate with powerful digital assistants that can instantly write structured poetry, debug highly complex software architecture, and deeply understand the nuance and intent of our multi-layered requests. This wasn't just some marginal improvement in software. It was a total phase transition in computational capability, entirely driven by the ability to mathematically map context at an incredible scale.
The entire landscape of artificial intelligence was fundamentally rewritten by this single architectural breakthrough just a few short years ago. By ditching the linear processing of the past, AI finally overcame its vanishing memory problem and unlocked the raw power of internet-scale parallel computing. And that forces a rather profound consideration. If transformers managed to upgrade AI's computational capability this dramatically since 2017, seamlessly expanding from text to vision to the very fabric of molecular biology, what will the next architectural upgrade unlock? Thank you so much for joining me for this explainer, and definitely keep your eyes on what this incredible technology does next.
Thanks for watching.